like this. I'll pull it up here. So yeah, it's the alpha thing, right? You're saying equation
by 8 or 9. So if alpha is equal to 1, then some of the terms become 0.
Yeah.
And also when alpha is equal to 1, then this likely to happen at bonds.
When alpha is 1, it's all interfacial, right?
Yeah.
So, and do you need the equation to talk about that, or?
You can just describe by describing this equation, right?
Yeah, it's figure 5, right? So alpha's 1, it's all interfacial. And then you get the largest grain size. So how is that?
The smallest grain size.
Oh, the smallest grain size. No, yeah, you get the smallest grain size when it's all interfacial. I mean, isn't it all right? If it's all interfacial, isn't the grain size kind of 0? There is no grain at that point. So that's just the system, I guess. That's just the mixture. It's all just that.
Yeah, the interfacial
substitutional alloy. That's it.
And interfacial actually doesn't contribute at all, kind of. Okay.
I'm not sure there's even a grain at that point. I mean,
Yeah,
why does it even have a value here? I guess that would be one issue. Like, why is it not? It shouldn't have any answer at that point. And then when alpha gets smaller, so the interfacial region gets smaller, you get a larger grain size. Is that answered in your equation? Or, I mean, the one's kind of a strange thing, but
for one, there will be still some contribution from bond between A, B, B.
Let's see. You're talking about equation 9, I guess, and 8 or 8. So if alpha could be 0.
And then the last term is 0. The second term is they have some contribution. First term is all the contribution.
No, if alpha is 1, this term's 0.
Yeah.
That's when it's all interface. When it's 0, there's no interface. And this thing, do these two terms cancel or something? No, this is a AABB. Those are the pure components. I don't know. I guess I'd have to go back and really look at this equation again. This is a negative number, right? Most of the time.
Yeah. For A is less than 1 is always negative.
And T is the surface, and IG is the area, right? And then the bulk is this B. And these two are the same thing. This is just the normal Hildebrandt thing, right? Energy. Except this is AB is modified by alpha.
If you are saying that when alpha equal to 1, AB is less like to be.
When what?
AB is less like to happen. Then bond between AB less like to happen.
When alpha's,
alpha equal to 1.
why? It's a random mixture, right?
Yeah.
I don't know. Basically, I just wanted you to dig into it like what you're doing. And so you can't get, I couldn't really get an answer that was consistent with what he saw. And my answer is that it would be the opposite dependence. So if you can get it to be the right dependence, I just wanted you to kind of dig into it. I don't think the answer I have is that it shouldn't behave that way. So, but maybe I'm wrong, but that's the way I see it. Should behave the opposite of that.
Maybe he fixed the result and derived the whole paper based on that.
It's pretty hard to tell, and there's a lot of room for wiggling around here. I mean, I'm still pretty bothered by that equation 12 or whatever. Like, there were two people that turned it in, and they both went through the derivation and got the answer I had, and they said like, oh, this obviously gives that equation. It doesn't, like the last step is wrong in both. It just doesn't connect, and you can say it, but it isn't true, So if you use this to minimize the whole thing, and if this was wrong, then in this business about the whatever it is, what does he say? The asymmetry or something, that the shape factor is proportional to D. I mean, that's a unitless number, the shape factor, no matter how you do it. The aspect ratio is the simplest one. So why would aspect ratio be proportional to D? What does that have to do with this even? I mean, right, the surface area changes if you have a different aspect ratio particle. That's true, because surface to volume is different for a rod than for a sphere. In that case, what's D then? So, I mean, I don't, that thing isn't in the other paper. It's not in 22, and it's not in the paper that 22 references, the octahedral thing. So I don't know, this whole thing bothers me. That's why I asked it, I guess, but where did this come from? Because you can easily get a derivation for what that should be. It's a pretty simple thing to do. And like the two people that turned it in kind of this morning, whatever, they had done that and they got the equation what it should be, I think, and then this isn't it. So I don't know, maybe you guys, so anyway, then that plot 5 could be wrong if he's minimizing to this function, In other words, that could be why, or one of the reasons why plot 5 is wrong, because plot 5 doesn't, the alpha thing doesn't make that much sense to me either. So it's good to start looking at papers at this stage and say like, this isn't right, that's a really important stage to get to. Instead of like, here's a textbook, read it, everything's right in it. I mean, so, because someone reviewed this, usually like 3 people reviewed it. So they send it out. So when you read a paper, you tell them like who your preferred referees would be, supposedly without any conflict. And then the editor has a list of, so he has a computer file of everybody that's ever reviewed and everybody that's ever submitted a paper. And he can cross-reference the terms and things and find someone to review it. So eventually you'll find someone, they're not paying them, so basically he'll find someone to volunteer to review it. So it's not necessarily that that's going to be a good review, and maybe they never checked equation 12. And we saw that with the typos in some of the other papers, right? That couldn't even understand it.
Maybe a grade student can review it.
Yeah. I mean, it's up to the editor, So the other thing is that you could submit to Nature, and you could submit to like whatever, any journal, and you could get the same review. You could have this Journal of Applied Physics. You could have the same referee. So one's like a really high cited journal, the other one's lower. Then like this is a pretty good journal, but it's like high mid-range, But anyway, so that it doesn't matter what journal the paper showed up in, the same people could have reviewed it. I mean, it isn't likely to get more difficult review in Nature. It's got to be a shorter format. It's got to be like a 3-page thing. So sometimes cramming stuff in doesn't work. But so you can't really trust anything at face value. And you have to, I mean, some things you can, right. Even if you can't understand all the equations, then you should be able to take their final plot, like plot 5, and say, like, does this make any sense? Does that make sense that as alpha gets larger, the grains get smaller? That should make sense. If his thing worked, it should kind of make logical sense. If not, then he's attacking logic, and there should be some reason for it. Right? But absent a reason that the logical conclusion didn't work, then you start to be suspect, and maybe then you go back and look at equation 12. He's got three things he's minimizing against. The easiest one to mess up on is the FIG, this one, because these other two are like mole fraction. And the rest of it is just Hildebrand equation. So that leads you directly to equation 12. And like, where did that come? That means everything is hanging on, and the other one's a mass balance. So I mean, like equation 12 is the logical place where things could fall apart here, I guess. So if you can't get it, just say the best you can get on it, you know. Don't, I mean, cut some time that you're gonna spend on this thing. Don't say the rest of my life, you know. It's like he's gonna have to, and it just try to make it logical what you say. And then if I come back and give you a low grade, come back and argue like, well, no one could humanly do that or whatever. Or whatever, you know. And I'll be kind on appeal. But maybe brutal on first glance at it. So just come back and say, like, you know, whatever. So don't kill yourself. And generally, that's a good rule of thumb. I worry about that sometimes. Like, you give people hard homeworks, and if people, like, you got to have some point where you know, walk away from it. So, but anyway, that didn't really answer. And I don't know about that equation. I'd have to sit down and really break it down to figure it out. But you might be onto something, like you could explain it with that equation 8 or whatever. I mean, definitely alpha is in that equation. So how's this, to get the grain size, you have to do those derivatives of this stuff. So then you have to take this, whatever you're saying about this, then say, how does that impact the minimization of that? You want to find a minimum in FIG, which is back to equation 12, and then minimization against the so what is it, XB and X something, 29 against XB and XIG, and he defines somewhere, he defines XB and XIG. I mean, it's the fractions of the where the stuff is, but it's got to do with the, let's see, I guess those are just decided. Anyway, whatever, you can figure it out, I think, you know. So in the end, like, so you're gonna say you're reviewing this, right? So maybe you skim through it and see what's going on, and then you have a rough idea what the picture is, like what he's doing, and then you're gonna go and say, like, then he's got the results, you know. So maybe you just skip ahead and go to the results and say, like, that all makes sense, you know, that agrees with what you would expect, whatever, like the 5 figure. And then you can go back and then check to see if the equations are all put together right, or if you mess something up. But if your gut check of it doesn't work, then you really say, like, well, I got to nail this guy, like, somehow. I got to go back and find. It's just like grading the homeworks, right, or the exams or whatever. It's like, maybe you just look, did they get the right answer? Then you skim through and say, yeah, everything looks like it filled. They didn't just cheat and copy it, you know. They kind of went through the right steps. And then that's it, it's done. That's an easy one. But if you go back and you see the answer's wrong from your logical perspective, it's exactly like grading homeworks. It's the same thing, right? And it's just as tedious, like, if you're going to do this, and they don't pay you and you get no credit for it. It isn't like you're publishing a paper and your name gets on it. So there's no benefit to it at all. You're just doing it as a service to the world or something. To say that things are, I don't know. So it's a system that's bound for corruption, right? Because first, mostly the editor, for the specific subject you're doing, he doesn't know who the experts are. So you have to tell him that. up front, and he's probably going to pick your people. And those people are going to be like someone you went to grad school with, someone you're working on homework with now, and like, so you don't, there's no computer connection between the two that would link through this thing, but there is an actual connection, So somehow, like I just reviewed a paper for a guy from Oak Ridge. He's retired now. And then he calls me up, oh, I'm going to be in town. You want to go for dinner? It's like, well, I'm reviewing your paper. And at first off, I know him, So it's corrupted even like that. So everything is some kind of levels of corruption here. It's also true of grants and things, like reviews of grants. So you get a panel of people, and it could be just ethnic too, like certain ethnic groups, like Greek guys are going to stick together. I mean, that's the way it is. Indian guys, not so much. Greek guys, absolutely. So yeah, it's crazy because you'd think that the Indian guys could rule the world if they just figured out, get together, but they don't. They don't do that. So, but maybe it's a British system, the British history of some kind of honor system or something, as they killed everyone and stole all your money.
They send you the paper to review without anybody's name on it.
No. That's not how it works.
That would probably be.
Yeah, that would be a logical thing to do. Yeah, but then the people at the top would get messed up with that. So they don't want that. Yeah, there's a reason why they don't do that. The system's rigged, more or less. I mean, all right, it's not that hard to get a paper published, so it isn't, and you get nothing out of it mostly. You get some small thing out of it. So it isn't like you're going to buy a new car. All right, if you're in China, you do buy a new car. Like if you get a paper in Nature in China, they give you like 100 grand or something. So you do buy a new car.
The government?
The government, yeah. That's why there's so many Chinese publications, and they're all targeting like the highest. I mean, it's one of the reasons. Also, there's more Chinese than anyone except Indians. So it's like basically there's more of them. I think there's 10 times the US or something, or I forget what it is, but basically in the same landmass. So it's kind of like there's a lot of Chinese. And there's this benefit that they pay them for the publications. So that helps too. And now at this point, like the Chinese, a lot of the editors of the journals are from China too. India never seemed to pull that off. Like maybe they didn't pay, 100 grand per paper or something, or maybe they didn't care, I mean, India's doing fine, right? Pretty much. I mean, the upper level or middle class or something is doing pretty good, but China's still, I mean, the housing's a big problem there, and the pay is really low, It's like I had a Chinese grad student. He didn't really do anything, but he came to the US because the rent was cheaper in the US than in China. Yeah, so he was here on a student visa and just like not really doing much, but kind of work in the stock market in China. And then so the rent was cheaper here. It's like rent is so expensive there, that's insane. Because the population density is so high. But anyway, I mean, India might be like that too. I don't know. You're from here anyway, right?
Yeah, I don't know anything about it.
Yeah. I don't know.
Rent's pretty not cheap here. I'll say that.
Yeah, well, it's worse, and it's going to get worse too. It's going to keep getting worse. Like, look at China. I mean, you look at these countries and you say like, oh, it's terrible there. And then wait 5 years, then you're going to find out like, oh, you should have bought a house now, because basically the house is going to be like $5 million.
They say China's got a pretty old population as well.
Because they have a negative, yeah.
Although they didn't say that.
Yeah, like they rank the per woman, how many kids, right? Africa is typically like 6 to 10. And then China's minus 0.5. It's like their population's declining.
One child policy.
Yeah, I mean that's ended, but basically they still follow that. Like that became their culture, Like in other words.
Right.
So anyway. Yeah, so anyway, who knows? All right, so hopefully that answers, it didn't answer or whatever. So just turn it in whenever it doesn't matter. Because we just have to, actually we just have let's see, so we have this homework for this thing. And then there's just the final homework, right, which is like an individual thing, so it'll include experimental and whatever. So I'll have two questions, like you can look at the old one from last year, like two questions. 14, do end of finals week, and there's something about Gibbs-Thompson equation, it's a surface thing. And there's something about what is this? Phase separation.
This is last year's.
Yeah, this is last year's homework, which it'll count as two homeworks.
So we might be able to start it now, technically, just not the experimental part.
Now I'm gonna make up a new one. I'll have a new one. It won't be this one.
But it'll be, part of it will be topics we've already covered.
Yeah.
Oh.
I mean, you can't start it till you have it, right? And I haven't started to look at writing it, so yeah, you can't really start it now. You could do these if you wanted, but probably not going to use the same one.
So we'll have like a week about
Like end of finals week, which is
second.
I mean, it's just so I can turn it in.
18th to last.
Yeah, like the 8th.
Yeah.
And then I'll try to give it to you after Thanksgiving, like
Semester ends Saturday, December 9th.
yeah, and then we got like a week to turn in grades, I think, like the 15th. So I think it has to be kind of in by whenever, the end of the semester, to make it kind of legitimate. So you should have plenty of time to do it, I think. I mean, if not, just say like I don't have enough time. I mean, even if you can't, like even afterwards, you could still do it because I can change grade up to like a year or something. It's just like a computer thing. So it doesn't matter. Like if you feel like whatever, all right, so we don't need this. Anyway, that's what it'll look like though. This business, right? So no, I wanted to get the PowerPoint here. Aaron's sitting at home. I have to say, enable editing. It should ask you about updates when you close it, not when you open it. No, it's like you never would want to update now. Anyway, so this section's about simulations. So, and then everyone that talks about simulations always shows something of this theme, like there's three. Actually, there's kind of four things, but basically there's quantum mechanics. So this is kind of like the electronic state part of simulations, right? So if you want to know the Fermi level or the band gap for electronic things like silicon and so a lot of people want to know that. Like if you're trying to make a photocell, some kind of semiconductor photocell thing, you need to know the band gap. So to do that, you start with like the Schrodinger equation, right, to get the waveform of the electrons. And then so you can only solve that for simple things. You can't solve that for a bulk chunk of metals or semiconductor, right? So you have to use some other methods to do that, kind of ways to cheat, right? So there's two kind of main ways to do that. One's this Hartree FOC, which is you make some assumptions and then you do an iterative process to find the solution and make it agree with. So it's just an iterative process until it stops changing, and then you reach the point where you take the answer from that. And the answer will be like a waveform, like a Schrödinger waveform for the electron cloud, right? And from that you can calculate. Basically, you can calculate everything. So you can calculate the band gap, but you can also calculate the heat capacity and the enthalpy and things like that. Right. So anyway, so I'm not going to really go through these in detail. They're somewhat in the book. So the book has an extra author who came in to do this part. So the authors of the book don't even know really much about this. Right. So anyway, so it is something you'll run into if you're doing like atomic scale understanding, like absorption phenomenon, say like Raman absorption from graphene or something, then you'd probably be thinking about maybe. So Hartree Fock is the original cheat that allows you to solve problems. Then the more modern cheat from the kind of 1980s and 90s is this density functional theory, which is it's one other way to get the waveform, right? So it's basically a series of equations that have to do with the electron density. So density functional means a function of the electron density. And then basically you solve it to try to get again, like the waveform of the electrons. So you can calculate the band gap for a semiconductor and some other things too, like catalytic activity. If you're doing catalysts, you'd be doing this. So you want to know like the ionization state of a metal and a catalyst and how that's going to interact with some organic molecule in a reaction. Then you'd be using these kind of functions, right? So it more or less tells you if something would happen or wouldn't happen. And then to engineer it, you'd need a larger scale structure. In other words, in order to access, say it was a catalyst and the molecules had to come to the surface, well, you'd need to put together some kind of structure, macroscopic structure, right, where the thing would fit together. And then below that, you'd have a mesoscopic structure, which would be like the nanoscale, right, where you could diffuse into it. And then below that, you have the atomic level structure, which is this kind of quantum mechanics thing. So this tells you like, can the chemical reaction happen or not? Like in what happens with the molecules when a molecule pulls in to the site, how does it organize and then react and then something comes off, right? So for that kind of thing, or for band gap things, and you need to resort to these kind of methods. So these are like the density functional theory. It's expensive, so you have to buy into some platform to run this. You're not going to write your own code for this, and then that entry fee is going to be like $100,000 to get a license for it for 1 year, right? So basically, there's no shareware for this. So it's powerful. You need it to do certain problems, but you're going to have cash on the barrelhead to do it. You can't just play around with it, right? So. And also it's really complicated, so you need to really study quantum mechanics to understand even what you're doing. So it's a whole nother course to even just get started in this. So it's important to materials, and you'll see that it tossed around quite a bit. Mostly we're just going to digest whatever comes out of it and just say you believe it or not, or is it of use, or you'll use it a number that came from density functional theory. And that number you'll plug into something else. All right, so those, all right, so those are basically this wave function kind of things. And then ab initio molecular dynamics is going to have to do with atoms, like starting with an atom, and then the actual electronic state of the atom and how the electronic states interact. So this is a higher level than density functional. Like density functional is the electron orbital, right? And this is how you build molecules. So all the molecular dynamics are going to involve a set of rules. So you have a set of positions and a set of velocities for all the things that are in there. There's going to be a set of potentials where the things interact with each other, right? So you can have simple potentials for like particles, which would be like 612 potential, or you can have like atomic potentials that have to do with these waveforms, basically. So you feed in the waveforms from the density functional into a molecular dynamics. That's an ab initio molecular dynamics. So you start with an atom, then the electronic structure of the atom, and then how those electronic structure atoms would interact if you put them into a box and let them shake. So they're going to have velocities, positions, and then that's going to decide the distance between the particles. Then you have some kind of an interaction potential based on the waveform. It's going to give you what their reaction to that is. What's the force that leads to the change in velocity, right? And then a change in position of the atoms. So this is kind of the original molecular dynamics because it has to do with atoms and molecules, right? And then there's another molecular dynamics that has nothing to do with that, but has the same format. So this molecular dynamics, so you have some odd potentials. So you have velocities, you have positions, but the interactions are some simpler interaction, not a waveform interaction. It's just be like, I mean, you could have coulombic interactions, like the charge times the other charge divided by the distance would give you like a potential between the particles, right? You can have other kinds of interactions like 612 potential, right? So molecular dynamics is like a general. So the homework is a molecular dynamics simulation, but it's not going to be dealing with any kind of waveforms, right? So there's two kinds. They both, the idea of them are the same thing. Like you just put everything in a box, let them move around however they want to go. The potentials decide they're going to let them cook until, so 1/2 mv squared would be like the energy, and kT's energy, so you can get the temperature from how fast they're moving. So you can watch the temperature change. So you start with the things in some kind of random configuration, and then you let them start in random velocities, right? And then you let them start hitting each other, and then you watch 1/2 mv squared for the entire system and plot it out and see how it's going to reach some number, like a flat number. So it's reached an equilibrium temperature, right? So that's kind of, or you could say, you can measure the density of the particles and say the density reaches an equilibrium number. So you look at some parameter of the system, and you let them just cook and move around until they reach and settle down, like until they reach some kind of constant number. They might never do that, or might be such a gradual approach to that constant number that it's kind of imperceptible that it hasn't reached equilibrium, right? So that's the problem with molecular dynamics. You never know when it's done. Like you can say, I waited so long, the computer burned, smoke was coming out of it. It's done. But you can't prove that it was done from this. I can say that number kind of plateaued out, but you don't know that if it's going to click up or something downstream somewhere.
You said it's random. How do you simulate randomness, or is it like pseudo random?
Oh, I mean, you can simulate randomness just by having a random number generator, right? So you're always going to have a random component in these. You're going to have this kind of random number that's going to be, that's basically how temperature acts. So temperature in space is always fluctuating around. So you have some random fluctuation in time and space of temperature, which is the kinetic energy, like the 1/2 mv squared. So you have to have a random number in the whole system to make it kind of work. But it can still reach equilibrium in time if you give it enough cycles. So in this kind of thing, like a dynamics, you're always going to have a time step. So if you're doing, you have a velocity, you have a position, and then there's a time step. So you let them move a certain distance, and then you calculate at that position all the potentials between all the different particles on it. And then you calculate the energy for the whole system, and then you can let it cook some more, right? So and then you're going to have a response to all those potentials, and it's going to change the velocity and the direction.
So if you do a smaller time step, the computing cost probably goes much higher, right?
Well, the time step is just an arbitrary step, so it doesn't really impact things. Like reaching equilibrium is a key thing. It doesn't matter really what the time step is. I mean, the velocity, everything is normalized to be unitless in the system. So you have like the size of the particles as sigma usually. And then like all the sizes of the distances between particles and the potentials are guided in units of sigma. And sigma isn't necessarily the size of an atom. It's just some number that you put in. So everything is normalized. There's nothing, even time doesn't have a So the
So
time
it's not
step
like
doesn't
time
either.
Step of 1 second. or how-
No,
It's just.
it can be if you can connect this whole system to something real. So if you can connect it back to something real, it can be a real time, and it'll be a nanosecond. Like of the whole time you ran it for a week on the supercomputer, it'll be like 20 nanoseconds. Yeah, so the whole thing running is going to be like almost nothing in our terms.
Okay.
So to say in 20 nanoseconds, oh, I plateaued out temperature. I mean, that's one problem with this, that's a pretty short length of time. That's the best that you can do. You're not going to get 100 nanoseconds. So basically there's a couple problems with like the dynamics. The other thing is the system, because you're looking at a finite system, even if it has 10,000 atoms in it, like a micron of air has like gazillion atoms, I don't know, trillions, right? So 10,000 isn't anywhere near anything real. So the system size isn't big enough to talk about thermodynamics. Thermodynamics has to be like an infinite system of little particles moving around. Right? Here you have a finite system, like seriously finite. And then also moving around forever, like in thermodynamics, and this is moving around for 10 nanoseconds if you're lucky. Right. So there's a couple of problems with molecular dynamics. On the other hand, like there's some pretty cool things you can do with it, So basically it kind of works, even though it maybe it shouldn't work. That's kind of the idea. So anyway, so then I talked about before, like Monte Carlo, which is so this is a slide on Monte Carlo here. I'll probably go through that a little bit. Basically, you're gonna make random changes to a system. So it's not a time step. It's actually just you do a change. Then you calculate the free energy of the whole system. And then if the free energy dropped, you accept that change. If free energy went up, you take e to the minus that energy difference divided by kT, and then compare that will be a probability 0 to 1, compare that to a random number, 0 to 1. And if your number's bigger or smaller than that random number, then you accept it. So there's some possibility to do things that are bad. And then the system, because of that, the system can actually achieve some kind of result. If you didn't have that, and you did Monte Carlo without that step, the system would just collapse down to 0. Like everything would just collapse down. Wouldn't be anything of any use, because the minimum energy would be the thing collapsed to nothing. So basically you need that randomness to give it enough room to kind of shake around. And it's comparing that energy difference to kT. It allows you to change the temperature and see phase separation. So that's what Monte Carlo is kind of used for, seeing phase separations. So you can do that with quantum mechanical systems, and you can do it with larger scale systems. Right. So, and then within this, we all the stuff we did for heat capacity, you can do dynamics for lattices, like just the stuff like the Bose-Einstein distribution, the exponential kT thing, and the partition function, all that for crystals. You can do lattice dynamics on it, which is kind of like molecular dynamics, except in the lattice. And they move around, and from that you can calculate like the spectra, the Raman and the Brillouin spectrum, and also other kinds of spectra like quasi-elastic neutron scattering spectra and things. So people do kind of molecular dynamics with a lattice system. It's generally molecular dynamics of things are freely moving around, and then this lattice dynamics are stuck together with springs, like basically the Hookean spring thing. Right, so, and molecular mechanics, energy minimization. I don't remember that one. I mean, I think that's just energy minimization. I think that's more like modeling than, that's not really simulation. Let's just do like in this paper that we just did. I mean, it does a minimization of the energy to find what the equivalent structure is going to be, like the size of the integrating thing.
I think it is the system's minimum energy.
Yeah.
Based on that, that's actually fixed, and based on that, all the calculations.
Okay, for this thing. So it is a simulation.
Yeah.
Okay, I don't know about that one.
I used to know someone that worked on those softwares that density function theory.
Okay,
So I always tell them that they actually set a minimum energy. And
Yeah.
based on that, actually, they can start the calculation.
okay. Well, maybe those two are linked or something. But anyway, so of this, uh, so this is still like just two scales, right? This is like quantum mechanics, and this would be molecular, and then slightly higher than molecular, like colloidal. And then when you go beyond that, so there's reasons that you would want to simulate things larger and larger and larger, right? So basically, beyond that, you can go to a thing called dissipative particle dynamics, which is the same thing as molecular dynamics, except that you don't use 612 potential. You use a simpler potential that allows you to do kind of larger clusters of things. So if you have a complicated potential function, it takes more computing power. If you have a simple one, it allows you to get to larger systems. Right, so that's this DPD simulations. So DPD and coarse grain are coupled. DPD is a potential function for coarse grain simulation. Coarse grain means that you aren't dealing with atoms, you're clustering atoms together into chunks. So say even usually people will coarse grain water because following all the waters in a system where you're looking at proteins that are huge. So you're looking at protein folding, say, or protein something, some kind of change in state of a protein, but it's surrounded by waters, and the waters really govern what's going on because all the entropy's in the water, right? So basically to deal with that kind of thing, we have one big thing and a bunch of little things. You would coarse grain the water. So you could coarse grain it all the way to say that it's just a background field. Like you could say there aren't any particles to it at all. It's just a background field, right? And then, or you could say that say 100 water atoms are going to be clustered together and there'll be one bead. It's like one kind of bead in your simulation is going to be 100 water atoms. Then your protein, you could break down the protein into chunks too, like hydrophilic, hydrophobic parts, right? So coarse graining means you're going to cluster together molecules. You can see the behavior on a larger scale. Then you try it. If it works, then you say like, this is the way to go. If it doesn't work, you start over again, or maybe make it less coarse grained. Right, so it's a little bit of a game of getting the answer that you want out of the things. Then there's a whole nother scheme of stuff going on. I'm not sure it has to do with thermodynamics. It kind of has to do with material modeling in some context, but like machine learning. So instead of trying to, it's kind of actually anti-thermodynamics, right? So you take the results of something that you can't understand, and you have so you have like, yes, so you have to take, so say you can get a system and you can parameterize it by doing diffraction, and you can get, and you don't understand Bragg's law at all, but you can see the diffraction pattern has 18 peaks in it. So you can get a peak position and a peak intensity, and you have 36 numbers, right? And then say you want to know like the conductivity of that, electrical conductivity. You have no idea like what electrical conductivity has to do with those 36 numbers that you have, right? But you can kind of, and it could be other measurements too, like you do an IR spectrometer or something, you have another 36 numbers. So you have 72 numbers that you can describe something. And you have like a couple outputs, like you have the conductivity as a function of frequency, say, right? So then you can kind of say, well, you can take all those numbers and you can normalize them so they can go from 0 to 1. And then you can put a weighting factor in front of each of those numbers, right? Like 10, 5, 0, 0.1, whatever. So you make a matrix of those weighting factors. So you have your 72 numbers, you have 72 weighting factors. And then you have your spectrum coming out, which is like, it's got a frequency range, so it's got a bunch of numbers too. So you basically have a matrix, you have a weighting matrix for all those numbers because it's going to affect each frequency too. So the whole 72 numbers affect that frequency, it also affects this frequency. So you have a matrix. It's frequency versus the 72 numbers. It's a pretty big matrix, right? And those are all the things you measured. For each sample, you have all those numbers. So you have 500 samples. So you have like 500 times 72 numbers. Then so you have matrices of all these matrices, right? So you're saying there's one of these matrices that rules the world. It's the right matrix. And with that right matrix, I can predict all those 500 samples. So you try one and it didn't work. So you change it, didn't work, change it, didn't work. And you try the next one. So finally you get it to kind of work, and you get the next one, you keep adjusting that matrix of parameters until you get it to work. You say, I've solved it. So then you take another 100 samples and you test your matrix, weighting matrix against that to say, I can predict what it's going to be based on this matrix. All right, so that's machine learning. You can predict what the future is going to be, even if you know, understand at all about diffraction, Bragg's law, or IR, anything, or thermodynamics, whatever. You don't know anything at all. All you know is that you can get this matrix and you can predict the thing that you're interested in, which is a conductivity spectrum, dielectric constant spectrum or something. Right. So that you're going to use to make radar or some crazy thing, right? So a radar resistive material. Not that I wrote a proposal on that, but I'm not proud of it. Anyway, so you can do it. That's called machine learning. It's an anti-science way of dealing with things, but it's pretty popular. You can imagine that this is really popular in business. Like companies love this because, all right, you don't have to hire anybody that understands anything at all. In fact, nobody's going to understand anything. And you have this secret transitional thing that's going to give you all the answers. So it's like a black box, kind of like the guy in the Wizard of Oz, and just going to give you whatever you want. So it's exactly what people want, you know, what a business person wants, because they don't really trust people that understand things. They trust just get the answer, get it out the door, that's it, then go off on their yacht somewhere. So it's like, this is the perfect answer. So if you want to sell something to people, just stick machine learning into it, no matter what you're doing. You know, and there's a group of people that will just love you for that. So anyway, and data mining obviously is part of that, right? So there's like, you see this business analytic, I think it's the second best in the country in the business school. It was one of the first formed, right? And all they do is like potato chips, like why is it crunchy or whatever. So they have the 72 parameters for potato chips. Did someone buy it or not? You know, the bag was yellow, you know, so, and then they just correlate that out and they tell like Procter and Gamble or somebody like what color to make the potato chip bag. Right. And then they're like, yeah, that works, you know. So anyway, that's coupling with data mining with machine learning. The problem, you know, the data mining is data that already exists. Like, so they're stealing things in a sense, and then putting it through a machine and kind of coming out with something of value. So in a sense, if they don't own the data that they use to do that, so there's a lot of legal arguments over this whole scheme. I mean, for instance, right now the screenwriters in California just, I think they just solved their whatever against the companies, right? Whoever makes films and stuff. But it's basically like they can take the scripts that they wrote, or they can take the actors' looks, right? And they can take a bunch of actors' looks and put them in and see people like that guy or don't like that guy. Then they can make another actor using this process. I mean, this is really useful for image processing where you have pixels, right? And basically it's set up as a grid of ones and zeros. So image processing is like exactly, this is all derived for image processing, really. So they can make a script, they can make the people as a mishmash of existing people. And the actors said like, no, you can't do that. You know, like you have to pay us for that if you do it. And they won on that. So basically there's a lot of legal things going on right now with the whole thing about data mining and machine learning and all that. So you can see like it can get out of control maybe. But Chat GPT is kind of like that too. It's the same thing. So you can do it with text, you can do it with images, you can do it with people, you can do it with whatever, anything, right? So you can do it also with diffraction data. So it's a kind of simulation, and the thing is like all these, so there's like a club of simulation people, and they're chasing after these little, like the cat chasing the laser, you know, it's just like that. So the data, this artificial intelligence, machine learning thing is another, like a different color laser over on the other side of the room, and they're all running towards that. So basically they also have these kind of, DPD was like that for a while. And then, so, but there's some things that people like you would, unless you're going to get into that kind of activity, you know, that you can just use, like this homework is one of those, like this. So you can use this molecular dynamics simulation. You don't need to really know anything except you have to figure out a little bit how the scripts are written to feed into it. Then the program does all the work and spits out an answer. And then you can say whether you like it or not. And then if it fits in with what your experimental measurements were, then that's pretty good. Like you can say, like I used like a dynamic simulations and it predicted what I saw, and then I can put things together with that. And you can change the parameters much easier in the molecular dynamics too than in the actual experiment. You can do things you couldn't do in an experiment. You know, so you can put in atoms that aren't real and see what. So basically, simulation gives you the ability to do whatever you can dream up. And it also, that's a positive and a negative, you know. So it's got kind of a double-edged sword to it. Anyway, so yeah, so you can also say, like, if you want to look at really large scale, then you can do what's it called? When you have the grid, what's that called? Continuum mechanics stuff. I have the word here somewhere. It'll come up to me. It's not. Anyway, so you can do larger scale kind of bulk simulations with forces and potentials that go into like a CAD diagram of structures. Finite element. That's what I was looking for. Thanks. So that's like the ultimate large scale is finite elements. Right. A bunch of the mechanical people doing finite element. Maybe you guys are doing it. I don't know, but that's definitely part of this whole scheme of things. So finite element is really like a bridge, or could be down to like maybe some kind of smaller scale thing, right? And then mesoscales is where people kind of get excited because you can get these kind of self-assembly things going on. And then these DPD things are really small, right? So you have it's actually a continuum and different techniques are being applied in the different regions of the thing. Like here. So there's a pretty good this thing. So this is a DPD for liquid crystal, like in a watch display, and like how when you put a field on it, and then the display goes black because molecules align and the birefringence changes. You have a polarizer at the top, across polars at the top and bottom, like he was talking about in the lab the other day. But right, so when you get when they align, you can get the light to pass through, and you can see your LCD display. Right, so but you can simulate that using this coarse grain DPD simulation. It looks pretty good. I mean, it's exactly what happens. Like when you put the field on in a nanosecond or 10 nanoseconds, the molecules align. So how does that happen? You know, so it kind of shows something, picture of how it might happen.
And that's just like one volume element, and then
it's one volume element with a field on it. This picture, yeah. I mean, in the same, this is the same as like a bulk. So a macroscopic system behaves the same way. That's the process through which it aligns. So say if you wanted to do like spectroscopy on these, polarized spectroscopy, you can see how these are each kind of a molecule. So a rigid rod molecule, it's got polar groups on one end. So basically, you can see it's not really a molecule, it's really like 10 green dots with 2 red dots. And the red dots have coulombic interaction, and the green dots are like hydrocarbons, so they don't.
It's like a cell membrane or something.
Could be anything. I mean, it could be anything. But basically, I think they're kind of looking at LCD displays here in this particular one. But you can do this. Like you could set this thing up yourself. Like it would take you like maybe a couple of weeks. Right. So this kind of thing, it looks pretty cool. You can do it yourself. So it's kind of useful to look at that. Anyway, so that's what this LAMPS thing. So LAMPS was a program molecular dynamics program was written by Sandia. So Sandia is the top dollar US national lab. But it's a secret lab, kind of. Right. So it's in Albuquerque. It's a national lab on a military base. So they have like go through a security, then you go and you get to the real security. And even within Sandia, there's another level of security where they make nuclear bombs and stuff. Right, so there's like 3 levels you have to go through with guys with M16s to get to the bomb part. But anyway, one part of it, so they have the largest supercomputer array in the world. They also have like a 20-story lathe that they can cut a single chunk of metal into a missile cone or something. And they have their own railroad track. They have a bunch of these solar concentrator arrays. They have 3 fusion reactors. So they have like everything, and no one goes there because it's a secret lab. So it's kind of weird. Anyway, there's a ton of money there, right? Unlimited money. So one thing they did, so part of these DOE labs is that like they want to, the US government, at least the president and some other higher level people want to have the ability to like quickly come online with like technology, kind of like the Manhattan Project, but without the lag period of kind of rounding up all the German scientists to work on it, right? So I think the idea is that they have these people in like idle mode, sitting around and give them the tools they're going to need to use to predict like where the missiles are going to fall. I mean, they're doing that too, but that's part of the reason they have all the computers. But anyway, they have these computers available, and in their spare time, they do things like they develop lamps. So lamps is a spin-off of a nuclear weapons program, you could say, in a sense. It's mostly used for biological things, and like that movie of the liquid crystals coming together. And that's what, but basically it was funded by DOE at Sandia, originally. So right, but you can just, it's shareware, so you can just click into it, and they have a whole thing where you can download the whole operating system for it, and they have manuals, and like so many people are using it that you can just Google, lamps code for liquid crystal. I think that would give you some like it'll probably just show you some code, example scripts. See, and then you can basically it'll give you the code to do that. So there's so many people using it that basically anything that you can kind of think of has already been done, and then or something close to it has been done, and all you have to do is go find that and like modify it a little bit, right? So that actually is probably the most, like once you write a thing and then everybody uses it, and then kind of everyone's doing kind of the same thing, that's really the most powerful thing. So there's other options and lamps to do this stuff, but because it's so widely used, it's like for molecular biology, people use CHARMS program. And then there's some others, there's Homid Blue, and there's a few others that you could use to do stuff. But because this thing is so widely used, that it's like the best thing, at least to start with. And if you need something more, like you can go that way. But anyway, so you can play around with it with the homework and kind of get the feel for how it works. It's mostly like not that interesting until you get to the final movie. So there's a thing called Ovid that'll interpret the output, the dump file of the lamps program. You can just open an Ovid, and Ovid's like a graphic display, and you can like watch the movie, like a movie was made in Ovid. So you just take the lamps will give you a bunch of time sequences of X, Y positions, the velocity, basically X, Y positions and velocity of all the particles in the system. And then it'll be like a sequence of shots of that, arrays of all the particles. And then that Ovid will just convert that into a color graphic thing of the things weaseling around. And you can do slices of it, things in Ovid. I mean, Ovid's got a pay for use one and a general free use one. So the general free one is good enough. The only reason to go for, so you have to write some code yourself if you want to actually do this. Like you say you're going to do the liquid crystal, you have to have the original arrangement of all the atoms in the system, right, to start with. So, I mean, Ovid won't do that for you, and lamps won't do that for you. So you have to write a program in some other thing to set up an array of all the 10,000 liquid crystal things. Just them pointing in some random direction. And fitting into the box more or less. Actually, they don't have to fit into the box. So you can let the lamps will let you kind of thermally equilibrate it so they move so that they aren't crossing each other. There's like a warm-up thing for it. And then you have a real startup system, and then you feed that into your like the dynamics thing. So anyway, so yeah, there's a lot to it, I guess. And it also, if you like computer games or something, it can suck you into it just like computer games. Like you can just start doing it and it's like, oh, it's 3 in the morning, you know, something like that. So basically there is a slight addiction danger to this business, to this computer simulation. It's good to go in and get out, I think, is a good point of it. So anyway, so there's this issue of like, so all these molecular dynamics things are going to have this kind of business about interactions, right? So binary interactions of all the things you put in, so ij are going to go to like however 10,000 that you put into the box. So it's also like at the edge of the box, if the atom moves out of the box, usually it has like it comes in the other side, right? So you have this like reflection thing, so that your box is actually kind of infinite, so that if it's touching something over there, it's actually touching something on this side. So if your box is large enough, that's probably good enough, you know, to make it look like it's an infinite system. So your ij for these calculations only have to be what's in the box. If it leaves a box, it comes back into the box. In other words, you don't lose things. And then you can see like it would go on, like if you did ternary and then quaternary, and it would just keep going. So basically all these potentials of particles will have a cutoff distance where it doesn't go anymore. Because each of these, like this calculation takes, you know, a second, this calculation takes a minute, this calculation takes an hour, this calculation takes a day. So you want to say like, I'm going to cut off at an hour, right? So, and then you find out, I mean, you could try different cutoff distances and say it doesn't make any difference. So I'm going to cut off like here. It's the same between ternary and quaternary. So I just do ternary so I can do a larger box with 100,000 instead of 10,000.
So for polymers, it might take like a really, really long time.
Yeah. Polymers can take a long time. Yeah. But it's doable though. I mean, all right, so there's various ways of dealing. So like on your PC, you can do most of this. Like all this homework you do on your PC. But then you can get a lab computer with a bunch of graphics cards in it. And then it basically, the graphic cards can simultaneously run. So you can kind of, it runs faster on graphic cards for some reasons. Basically, you stack up a bunch of graphic cards in a computer, and then you can get something like, you know, maybe 100 to 1,000 times better than your PC, right? And then if that's not enough, so if it's taking you too long, you can do that. Or you can find someone who has one, like Nichols has a couple of these computers, you can use his.
People with gaming PCs.
Yeah, you can just find someone with gaming PCs and say, I'm going to use it, you know, and during the day when you're asleep, you know? And then like, so, and then like Ohio Supercomputer lets you have 1 hour of computer time or something, which turns out that's enough to do a PhD on, basically, if you know what you're doing. So if you try it out first on your laptop and then try it out on Nichols things, and then when you really want to run it, go to that. Basically that 1 hour is probably pretty close to enough to do the whole thing. Because your whole thing's going to run like milliseconds on a supercomputer. You know, so basically an hour is a really long time. You know, and then if not, you can get money and pay him for it. I think it's like, I don't know, it's not much. It's a couple $1,000 an hour or something. And in this very, like Ohio Super, yeah, but an hour, like I said, it's going to be milliseconds. It's going to be your runtime. It's like that hour. That's all you're going to need. You know? And if that isn't enough, you can go to, like Oak Ridge has a free user thing with their computers. You can also go to this. Google has a bunch of banks of graphic card computers, just Colab. So you can put your stuff on Colab and then run the lamps on Colab for free. You know, it's like a free supercomputer bank. I think it's in Iowa. You can
So
just
you're like
kind of,
running it remotely.
yeah, you run it, all the stuff you kind of run remotely, once you get beyond your PC. Like you would never go to Nichols Lab to do it, you do it over the, remotely.
Right.
Because you just have a text file, it's maybe like 100K. You're gonna send that over, and then the thing just runs it, and it's gonna spit back these array files, it's gonna be maybe like 1 meg, if that, maybe a lot less than that. And then you're gonna feed that into Ovid on your PC and watch a movie. So yeah, there's no reason to be in the same room as a computer. And then, so you can run it anywhere kind of in the world if you want. So if you can find a friend somewhere, you can just run it on theirs, So it isn't like that constrained. The first thing is like figuring out like what, on a small scale, like what's going on, like how you'd want to do it. So you'll see in this homework, you'll see like how that works. I mean, if you get through it. And anyway, so there's always going to be like a cutoff distance for the interactions of the thing. So basically, because you can't keep going forever, and it doesn't matter. Like at some point, you'll find out it doesn't make any difference. So that's where you cut it off to cut off your calculations. And then it's just a series of these. So like force is for spring is a spring constant times a distance. And then if you take the integrate, so force is derivative of energy per distance. So if you integrate, you get distance squared divided by 2 times the spring constant. So you'll see this kind of potential. This would be a bond, like a chemical bond in a molecule, right? So you can have tensile deformation of the bond, and you can have rotational deformation, and it's the same format. It's like you would have like a kind of a rotational spring constant times the angle would be the force, and the integral of that gives you the angle squared by 2. Like, so you'll see that kind of term all over the place. Something squared times a constant. And the constant is going to be the modulus or the spring constant of whatever's going on. Then there's some other kind of more complicated things about angular dependence, right? Like if you have two angles, you have say you have carbon carbon, another carbon carbon, and then another carbon carbon. So you have that angle, and you have this angle over here too, and those things are related to each other. So if you look at the energy of butane, it's going to depend on the rotation of both of those angles, right? It's going to have these peaks and valleys when the things are trans and cis and like that. But anyway, so there's functions for that. But these are all coded, like LAMPS already has all these things in it. Like, so it's just plug and play, really. So it'll ask you for these constants. Like what's the spring constant for the bond? So those will be standard input, and they have to be in exactly the LAMPS format for it to consume it. And then there's like Coulombic interactions. So you have like a dielectric constant to govern it. So you just have 1 over R for the Coulombic, and then the charge is squared. And then the standard like 612. So the 6 can be calculated. That's the van der Waal long range thing. This kind of sweeping up. And then this one is just made up. The 12 is a made up thing. So that's the wall. That's the hard core. So that can be substituted for an exponential, but generally, like this is the function for like close range interactions. So this is the thing like the Schrodinger equation would take care of if you were going that route. But if you're doing a simulation, then you just have this one energy of interaction parameter. And if you're doing a molecular dynamics simulation, you just have this energy of interaction, and the 612 potential gives you this kind of well. And sigma, let's see. There's a sigma in this thing. That's the separation distance. Sigma is the minimum in this thing. Sigma ij is the weld point, like where the things want to be. Right, so basically your size, this will just be one number, like all the distances will be normalized by that sigma. So it'll just be like one number input. So you don't actually have distances, you just have units of things, and then afterwards you convert it by sigma to what the actual physical distance is. So everything is going to be a unitless number, and then it's going to be converted back to reality through some numbers that you get from a measurement. This is from a book, like he's saying the same thing. This is this Buckingham So 612, but you replace the 12 with this exponential, which is almost the same function. So it's just like a preference. Anyway, that's your energy minimization thing. But anyway, we did that in this homework, but I don't know how that involves with this thing, but what are we doing now? Oh, this is lattice dynamics, right? So this is exactly what we did for heat capacity, like just the partition function, log of the partition function to get the energy, the 0 point energy, and then gives a harmonic oscillator for the bond. Then that's valid within 2/3 of the melting temperature, and then apply this solution that we had from the Dubai model, and then basically from that, putting that into a computer, so it's a lattice dynamics. It's like molecular dynamics. Everything's moving with a frequency, and then you let it equilibrate. So your starting point would be some kind of grid, and then let them all shake. Then you let the volume of the system change, and you can get the thermal expansion coefficient as a function of temperature. And you can get it's possible that like this group got the thermal expansion coefficient. They predicted it like perfectly, right, for this fluorinated manganese. Right? So anyway, so they're working below the whatever the cutoff is, be 1004. So this is a cutoff that it works up to that point. It deviates because of the anharmonic vibrations in the lattice. So that's one thing you can do. I think this Allen guy is the guy who wrote this chapter in the book. I think they got it's two Norwegian guys or something, and this one British guy that shows up that wrote this chapter. So that might be Allen. Anyway, so you can kind of see where he's coming from here. So you can predict that. You can also predict like all the rest of the heat capacity from the molecular dynamics. So you do the molecular dynamics, and you can predict all the thermodynamic properties from it. This is what is this thing? Is that the same Allen paper? No, right. So this is the same system, I guess, that fluorinated. Oh no, this is an alloy of magnesium and manganese oxide, right? And then so it's like a mixing, calculating the free energy of mixing, or like basically the phase diagram would be the minima of those two. So this is at one temperature. You'd run it at a bunch of temperatures and get the phase diagram from that, from these minima, wherever they shift around. So this is just like Bose-Einstein averaging to get the average properties. And then so yeah, so in this simulation, he varied it's what it says. He varies the cell size, calculates these average properties, and he finds where the properties converge. And then that's the property that he takes as the thermodynamic property of the system. Fixed unit cell size. Oh, I see. Cell size, he starts with a cubic cell, then he goes to like 4 of those and 8 of those and 64 of those. So it's the same system. He's just making it a larger and larger system until these numbers reach a flat value. In other words, the system doesn't change with system size. And then he takes that value. So this is just basically a calculation he's doing from knowing the frequency, and then just spits out these curves, right, from that. from varying the cell size. This is more or less like a calculation, not a simulation. All right, so this is also from the book. So, so this is just how you apply the Monte Carlo to get just using Monte Carlo with the same kind of approach, like the heat capacity things we did. So, like this is so Z isn't the partition function. Z's a state, a position of the state. Like in other words, he's got this alloy with the two metals, and then if you can change, say you have a box and you have magnesium and manganese in different points in the box, then you can move those around. So one state would be with them all in one position at one concentration, then move them around to another position. So that'd be a different state. So you can have a bunch of different possible states, a bunch of different Z's in this thing. Each one's going to have an energy, right? So for one state, PZ is the probability of that state. It's going to be the Boltzmann factor and then divided by the partition function, right? The sum of states, and then that will give you the probability of that state. And then whatever parameter you want to get, you use that probability to give you the parameter. So that's just what we did before, right? Except that he's going to calculate, he's going to move the atoms at random, then calculate the free energy. And then Q is going to be the free energy. And he's going to say, like, did that random change of position lower the free energy? If it did, he accepts that new position, then he moves it again. Did it lower it? Yes, it did. Accept it, move again. Did it lower it? No, it didn't. And then at that point, you compare the probability with the energy change that you had for that state by KT with a random number, and that you either accept it or don't accept it based on that comparison. So that's the metropolis using this kind of this scheme of the partition function. Right? So anyway, so that's in the book, basically. It's the same kind of thing. Oh, it goes through it step by step here, but so it's the same thing. Anyway, that's just the metropolis Monte Carlo approach, right, to doing a simulation. So there's no time step in this. It's just random motion of things, random swapping of positions of things, and calculating the free energy. So it's not a time step. It's just like testing every possible arrangement of everything. Right. This kind of simulation, all right, LAMMPS does this. LAMMPS will do a Monte Carlo for you, but basically, generally you can write your own code to do this. Like it's not hard to write a Monte Carlo code, right? Because every kind of software, like BASIC or whatever you're using, will have a random number generator. And that's really all you need. And it has to have an exponential function in it. And other than that, there's not much else to do with it. I mean, you have to calculate all the interactions between the boxes and the thing. So there's apps like this icing simulation app you can get on your phone, and it'll do the icing model. And you can write a code pretty easily. Like when I did characterization lab, we wrote a code to do this. It's easy. It's not hard to do. For 2D, it's simpler than 3D. Like 3D is a bit more, but 2D is pretty easy to do. And you can see, like, you can vary the temperature because it's going to be per KT, so the temperature is going to govern your decision whether to accept or not accept. So you can get a phase separation from it. So this looks a lot like spinodal. You get spinodal structures. So again, it's also a matter of how many steps. So you're going to watch. So this is a plot of the, I guess, the free energy difference, and like initial step, and then the free energy is dropping. So you say, yes, I accept, yes, I accept, yes, I accept. And then free energy drops, and you're doing this random step also. And eventually it's going to reach like an equilibrium. So again, like, it's a question of where is equilibrium? I mean, how many steps do you actually have to do to reach equilibrium? When you do the 2D, you'll see it's going through all kinds of transformations. And it's not clear like what the final structure is you're going to get out of this. Like you have to just decide I'm done and that's it, and this is what it looks like. And then you can compare different systems, but basically there is a question of did you reach equilibrium? So anytime if you review a paper on this kind of molecular dynamics or Monte Carlo, the first question you ask them is, how do you know you reached equilibrium? Like, how do I believe? Like, you have to convince me that you reached equilibrium. That's the first critique, right? That's number one on the list. Yeah, that's supposed to just go through like how you do the Monte Carlo. This goes through how you do the molecular dynamics, which is what the LAMPS code is for this, the homework. But somehow so setting up an initial condition is kind of, so you set up something and usually you do a warm up to get it to be in a reasonable, like the way you set it up, it could be that the atoms cross each other, right? So you have it, throw that into the lamps and it'll have a thing that says no crossing molecules, and you can let it run for a little while and it'll figure out like what the positions are to not cross. So it hasn't reached equilibrium, but it's a place where you could start the simulation, right? So the thing you make doesn't have to be perfect. You can let it kind of shake it around and get it so that it doesn't have problems like molecules existing in the same space. Because particularly like the DPD simulation, the molecules can pass through each other because it doesn't have a hardcore potential. So anyway, so generating initial condition, that's a whole thing to think about a little bit. Like the lamps isn't going to do that for you. You have to come in with something that's got your box and all that, some kind of initial position of everything. Then if you write a paper from, you have to say what the initial condition was. So you can say, how did that impact the result? Then yeah, you have the potential, so you can calculate the force, and then from that you can get and then you usually have a starting set of free energies, but then the starting set of velocities, and the new velocity at t plus delta t is going to be the old velocity plus the force divided by the mass times its time step. So basically you change the velocity every step and you change the position. It'll be like the velocity times the time step gives you a new position, add to the original. And then you just keep repeating that. And while you do that, you monitor the temperature, which is the velocity squared, how that goes with that basically is velocity squared, right? Sum of all the velocities squared. And then that should follow a scheme like this, like the temperature is high and then it's going to like drop down and we'll reach some value at some point over a certain number of steps. And in this case, they are time steps because you're doing velocity. Right? So, and then you have whatever the positions, then you can calculate things like the diffusion coefficient if you want. Like how much did it move as a function of time would give you the diffusion coefficient. All right, so when do we quit there? We're out of time. So on slide 15. So I'll finish through. There's not that many slides here, so I'll zip through this next time and I'll go through I guess on Tuesday, I'll go through the homework. And it's due like nominally due on Wednesday, but like it's Thanksgiving, so you can kind of, if you want to ruin Thanksgiving, you can drag it out, you know. But if you don't, we won't meet again till the next Tuesday. So maybe the Monday. That would be good to have it by Monday at least, yeah.
So no, there's an exam that day.
All right, well, whatever. I mean, it's a whole week, right? So should be able to find some time. All right.
It'll be fun.
Okay. All right.
But yeah, people leave it over the break, then it might be published.
Yeah, because no one then well, I put down Hugo, you can try to reach and see if he gets back. There's another guy that's good at this stuff that you can talk to, grad student. But Hugo, he works for Nichols, so anyway,